Hi everybody, welcome to another video in Calculus 2. We go to section 12.3, actually 12.3, not 11. 12.3. We will study calculus in polar coordinates. We review polar coordinates previous section. Now this time we'll study about the calculus. First, slope of the tangent line or the derivative. Alright, suppose f is a differentiable function at theta naught, and the slope of the tangent line to the curve. Now the curve will be given by the form r is a function of theta, and the derivative in terms of y and x will be given by that. And every time we have a quotient, the denominator cannot equal to 0. And when we have the function equal to 0 and the derivative is not equal to 0, then we have the tangent line theta equal to theta naught, meaning the tangent line go through the pole. Yeah, for that line, theta equal to theta naught is the line that go through the pole, and the slope is equal to that. Right. Now, formula is nice and all, but it will be better if we just do the problem without the formula. There's a better reason for it. So, this is in section 12.1 on page 122. We have derivative for parametric curve. If x is a function of t and y is a function of t, derivative dy over dx will be given by derivative of y over derivative of x, both with respect to t. This is a lot easier to do than try to memorize that. So that's exactly what we'll do. Right. So first, in polar coordinate, we have x is r cosine theta. Now we know that r, the curve r, is a function of theta, so we'll replace f of theta into r. And then similarly, y is r sine theta, or the function sine theta. Right, because the curve r equal to f times the function of theta. Sorry. Now we take derivative dy over dx. As mentioned before, both of them, x and y, are function of theta, so we can take derivative of theta, derivative of y with respect to theta, over derivative of x with respect to theta. Right. Now this is just the step where we need to be a little careful. Derivative of y over derivative of x with respect to theta. So derivative of y, which is f of theta sine theta, that is y, over derivative of x with respect to theta. Simple enough, right? Since both of them are product, we use the product rule. And now we just take derivative. It's a product, derivative of theta, so f prime theta, so u prime v plus u v prime derivative of sine is cosine. And then this is not a quotient rule. We have a product rule on the top and a product rule at the bottom. So derivative, product rule at the bottom, u prime v plus u, derivative of cosine is negative sine, and multiply it out, that becomes negative. And then, so as you see, this is a lot easier to do than trying to memorize this and not understand it. Right. So my advice is just write down what is x and what is y as a function of theta, and then we take derivative and divide them. Just make sure that we put y and x in accordingly. Yeah, just need to be careful on that. It should be easy, right? Right. Let's look at a couple of samples. Find the slope of the tangent line to the circle that. Right. So just write down what is x and what is y. So x is equal to r cosine theta. R is 10, so we have 10 cosine theta. Y is r sine theta. R is 10 sine theta. And then we have derivative dy over dx is derivative of y with respect to theta over derivative of x with respect to theta. Right. My advice is actually write out derivative of y. So this is y. And then derivative of x. Derivative of 10 sine is 10 cosine. And derivative of 10 cosine is negative 10 sine theta. 10 and 10 cancel out. Cosine over sine is negative cotangent. Yeah. Yeah. So just like that. Right. Yeah, just write down x and y, and then use that formula instead of that formula. And just a product rule. Right, next, find the point on the interval from negative pi to pi, so that the chaoid has a vertical tangent or the horizontal tangent. So first we will find derivative, and then we'll determine vertical and horizontal tangent after that. Right. Sounds simple enough. So first, let's write down what is x, what is y. X equal to r cosine theta. R is this function, 1 minus cosine theta. That is r, and then cosine theta. y is r sine theta, r is 1 minus cosine theta, and then sine theta. Right, so derivative is derivative of y with respect to theta over derivative of x with respect to theta. Right, so write down derivative of y with respect to theta. This is y. The sine theta. And then x is that. Right. And of course we use the product rule for both top and the bottom. U prime v plus u v prime. Right. Right. Now, derivative of u, derivative of negative cosine is sine. Derivative of 1 is 0, so we just have sine theta times v. And then plus u v prime, derivative of sine is cosine. Right. And then the bottom, u prime, derivative of this, once again, it's just sine theta. And then v, then plus u, derivative of cosine is negative sine. Right. We have sine square plus cosine theta minus cosine square. And then at the bottom, sine cosine minus sine theta, and then plus sine cosine. Right. Yeah, a few things we can do here. Combine like term is the bottom, and then sine square and cosine square, we can rewrite sine square as follows. So we have cosine square plus sine square is 1. So sine square is 1 minus cosine square. And we substitute that into sine square here. Right, sine square is 1 minus cosine square. And then we have plus cosine minus cosine square. Combine like terms give us 2 sine theta cosine theta. minus sine theta. Right. And then so we just have 1 plus cosine theta minus 2 cosine square. And the bottom we have 2 sine theta cosine theta minus sine theta. Right. So that is the derivative. Now if we want the horizontal tangent, we'll be able to run out of space to solve it because that's quite complicated here. But if we want the horizontal tangent line, we will have derivative equal to 0. So I will write this down. If we want horizontal tangent, meaning that we want the derivative equal to 0. If derivative equal to 0, we have a quotient. That means the top is equal to 0. Which means if we want it, we will solve for this. I won't have enough space to do it. But we solve that equal to 0. And we find theta. And for vertical tangent line, dy over the x equal to 0. I'm sorry. The vertical tangent line, the derivative does not exist. Derivative does not exist, meaning the bottom equal to 0. So in that case, we have 2 sine theta cosine theta minus sine theta equal to 0. So the top equal to 0, the derivative equal to 0, horizontal tangent line. The vertical tangent line, derivative does not exist, where the bottom equal to 0. Right, we solve for that. Now, if there is potentially any values that make both the top equal to 0 and bottom to 0, in that case, we have to factor out from the top and then simply find that. That could be the case. Like I said, if the top and bottom equal to 0, that is kind of indeterminate. But which means they will share a common factor, so we can cancel those common factors and simply find the problem. But that's what we do here. The point here, of course, is how do we take derivative. And so I said, just dy over the x is derivative of y with respect to theta over derivative of x with respect to theta, and then we simplify if we need to. And then horizontal and vertical tangent, that's what we do. But then there may be a case where both the top and bottom equal to 0, which just means that they will share a common factor. Cancel those first, and then we do this again. Right. So the first part of calculus is derivative, which is equivalent to the interpretation is a slope. Now we go to the second part, the integral. The interpretation, of course, the area under the curve, but in polar form, it's quite different. Right, area of region bounded by polar curves. So first of all, polar curve, so there be more than one. So let R be the region bounded by the graph of R equal to f of theta and R equal to g of theta. So we have two functions. The function on the outside is R equal to f of theta, and the function in the inside is R g of theta. And we want to find the area between the two polar curves. And not only that, it is bounded by 2. One of them is theta equal to beta, and the other one is theta equal to alpha. And the formula is given by that. So first of all, why do we have this? Actually, this is not that difficult. Think about if we just have the most basic one. It's just a sector. So if let's say we have the portion of a circle, I'm just going to draw it. So we have this part. So you have this sector, we have the center here, both of them are radii and the angle theta. So what is the area of this sector? So the area of the sector is 1/2 r squared theta. Right? Or if we think about this, now think about this just like a triangle where we have the base and then the height. Yeah, just imagine that this is flat. This is flat. We have a triangle. So we have 1/2 base times height. But this is the base. It's not actually a straight line. We can use S, which is the arc length. 1/2 S times the height. So kind of like a triangle, right? But this is S instead of the base. The arc length S is r theta. And the height is also the radius r. So we have 1/2 r squared theta. So for one segment is that. Now, if we want to have another smaller, and then we find the area of that segment, it's also 1/2 little r theta, r squared theta, and then we subtract the 2. That's why we subtract the 2, and we have that. So it just have a big sector minus a little sector, and the area left is the area in here. Right. So the goal here is to determine the outer function and then the inner function, and then the limits. Now this time the limit, to determine the limit, is a bit more difficult. Right. Now let's look at the first example. Find the area of the 4 leaf rows. So we want to find the area of that. Actually, we can graph that as well. Make sure it's in the polar mode radian. Right, let's graph 2 cosine of 2 theta. Right. Kind of small, right? Let's zoom in. Better. How about we make that look like a square? The increment on the x and y are the same, so that's why we have that rule is better. So we try to find the area of the whole thing here. Now, notice that if we want to find the area of the whole thing, this is the same as the area of one of the petal multiplied by 4, right? So if we just find the area of one petal multiplied by 4. Even better, each petal is symmetry by itself. So if we just find the area of 1/2 of the petal, just find the area of that, multiply by 8, right? So first thing we say the area I'm just going to draw it instead. So the area of that equal to A times the area of half a petal. Yeah, A times the area of half a petal. I should draw that bigger, but get the idea, right? So we find the area A of this. Now, nice to know, but how do we find the limits, right? So, first, notice that when we draw the petal, we start from 0, r equal to 0, going out, and then back, out, and then back, out, and then back. So, potentially, we have to find all the points where the r equal to 0. So, pretty much to find the boundary, we let r equal to 0. So r equal to 0. In this case, the boundary is 0. So we do that. We have 2 cosine of 2 theta equal to 0. Now cosine equal to 0. In the unit circle, this point and this point cosine equal to 0 for those points. So from here we say pi over 2 over 3 pi over 2. We can do that, however, because of the multiple angle here. So in general, I will write as follows. 2 theta equal to pi over 2, and then add the pi to it, right? From here you add the pi, then add the pi. We'll just say pi over 2 plus, that's fine, plus k pi. So, meaning that pi over 2, 3 pi over 2, 5 pi over 2, and so on. And then so on, right? Yeah, pi over 2, add a pi to it, we have this point cosine also equal to 0. Add another pi, go back to this point also equal to 0. Add the pi, just keep adding a pi to it. And divide everything by 2. So we have theta over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So indeed, if we have to, we can say we have pi over 4 is one boundary, and then the other one is negative pi over 4 or 7 pi over 4. We can take just 7 pi over 4. But if we go from here to there counterclockwise, we will use negative pi over 4 instead. But we not even use that. What we use is the limit though. Go from here, theta equal to 0. So 0 to pi over 4. And then 0. Now, we have the nice row parallel there. I will change the limit to 0 to pi over 4 to make sure that actually the limit that we have. So 0 to pi over 4. So always do that. So we know that indeed we have 1/8 of the rose petal, right? Rose. And so the area will be 8 times. So the area of the whole rose petal is equal 8 times the area of one parallel. The limit for the integral will go from 0 to pi over 4. Now, for this rose petal, we go from the center and going out, looking outside from from the pole outside. Well, what function do we see inside, and then what function we see on the outside? So, like if we look from the center, looking outward, we see this function first, and we see that function later. Same thing here. We look from the pole, we don't see any function inside, but we only see the function outside is that function. Right? By the way, the formula is going to be, don't forget there's an 8 in front of it. Right. So for the area of the polar curve, it's going to be 1/2 like I said, looking outside from the pole, the only function we see on the outside is that. So we have 1/2 of that one square and then the inner function from the pole looking outside, we don't see any function from the inside, so that will be 0. No function in the from the inside. Right. Now just integrate this. A times I will bring down to 1/2, and then that one square will be 4 cosine square of 2 theta. Now, most of this problem we will use the power reducing identities. So power reducing cosine square is 1 minus 1 plus cosine of 2 theta 2a over 2, and sine square 1 minus cosine that power reducing we use a lot in this section. Right. So cosine square reduce the power, double the angle, reduce the power, double the angle. Cosine square will be plus, sine square minus. Right. So simplify this, we have 4 8 times 1/2, and then there's still a 4 here, right? That 4 because of the 2 square. I'll take the 1/2 on the outside. Right, and then use that identity. So we have 1 plus double the angle, 2 theta becomes 4 theta, then divide by 2 d theta. Right. Now take all the constant on the outside. Four on the outside, 2 on the outside. We will have 4 times 4 and then 2 at the bottom, right? And then integral from 0 to pi over 4, 1 plus cosine of 4 theta d theta. Right, now that's easy. That's 8. Now integral of 1 is theta integral cosine of 4 theta is going to be sine of 4 theta over 4 integral from 0, limit from 0 to pi over 4. Right, and then so we just substitute in the limit 8, we have pi over 4 plus sine of 4 pi over 4 divided by 4. Subtract 8. Now put in 0. Sine of 4 times 0 over 4. Now, this is sine of pi, which is 0. And then sine of 0 is also 0. So those are cancelled out. And we have 8 times pi over 4, so it will be 2 pi. And then 8 times 0, so just 0. So pretty much, yes, just 2 pi. Right. Now, we can confirm that by just do math. Option number 9. We go from 0 to pi over 4. And then, we still have the 8 in front of it. Second, insert 8 times. Right. Now inside we have 1/2, 0.5 times 2 cosine 2 theta square. Actually, we enter the y1, right? We can just use y1 square if you want to. Alpha trace. That one, right? Square. Yeah, pretty much that. I see. Yeah, that is 2 times pi, definitely. Right, so we got. So, before we do this, make sure we actually draw the graph and determine the limits. We determine the limits, so we graph it first and make sure that actually the area that we want to, and then we can just go from there. Right, so the first example. Next, set up the integral to calculate the area inside the inner loop of the limit on 2 plus 4 cosine theta. So in this case, we only want this area. Not the whole thing. But first, let's put in the function 2 plus 4 cosine theta. We might need to zoom out. Windows from 0 to 2 pi. Right. Let's zoom out. So there's an inner loop. Right. So first, how do we find the limit? So we just need to draw the inner loop. So how do we determine that limit? Right. So remember, when we get back to here, we start from r equal to 0 and on out, and then back to r equal to 0. So pretty much we will set r equal to 0 and we solve it. With that, we find the limits. Right. So first we find boundaries. For this one, when r equal to 0, two plus 4 cosine equal to 0. So cosine equal to negative 2 over 4, or negative 1/2. So we need to solve for cosine equal to negative 1/2. So on the unit circle where cosine is negative 1/2. Right, cosine is the x values negative 1/2. So we have one values here and one values there. So let's determine those. If we use the inverse trig function, we should keep in the degree mode. It is easier to see which one is that. So we take cosine inverse of negative 1/2. And that gives us 120 degrees, which is 2 pi over 3. So yes, 1 point 2 pi over 3. And the other one is opposite from that, from the polar axis. So that is 120, and then we go negative 120 or 240. So this point is going to be either that or 4 pi over 3. Right. So when we solve for that, we have theta equal to, we can do cosine inverse of negative 1/2 plus, we can go around and around 2k pi, or we can also have the positive or the negative. So that is the solution for the cosine equal to a constant. So with that we have the positive theta or the negative theta. Both of them give us the same values. Anyway, so for that, so we have theta equal to 2 pi over 3, 4 pi over 3, and I'm going to write dot dot dot, meaning that if we want to, we can find a few more of this, because when we have the point here, go extra revolution. As long as we stop here, the cosine equal to negative 1/2. So I can add 2 pi to here, subtract 2 pi from here, we still have the same angle. Right, so those are boundary. Now once we have the boundary, put on the graph and see if actually what we have won. 2 pi divided by 3 to 4 pi divided by 3. It didn't graph anything, right? Because when we graph, have to be in radian mode, right? Just be careful with the calculator. Right, so that inner loop. Let's zoom in. Yeah, so that's just the inner loop. Right. Now once again, if we want the whole thing will be from 0 to 2 pi. Typical, because that the period for cosine is 2 pi, so we have the whole thing. But if we just want the inner loop, 2 pi over 3 to 4 pi over 3, we can use the symmetry if we want to. In that case, we just go 2 pi over 3 to pi. But that's not, we don't need to do that. Now we just have the inner loop. Perfect. So the area is equal to, we know the limit now is 2 pi over 3 and 4 pi over 3. And the formula is 1/2 the outer radius square over the inner minus the inner radius square. So the outer radius from the center, from the pole looking out, we don't see any function from the inside. We only see one boundary on the outside. So in that case, we will take the function on the boundary, which is 2 plus 4 cosine theta square. and then subtract the inner radius. There's no inner radius, the inner function. So we have 1/2 integral from 2 pi over 3, 4 pi over 3. I'll take the 1/2 outside and we just have 2 plus 4 cosine theta square d theta. Now this one we only need to set up the integral. So that's how we set up. Of course, multiply this out and integrate. It's not that difficult. But the interesting part here is how do we set up the integral. Right. So be just that. More example. Consider the circle r equal to 1 and the carryoid 1 plus cosine theta. Set up the integral that calculates the area of the region inside the circle and inside the carryoid. So first, let's just draw a circle. R equal to 1. And then the carryoid. Right, so we have those graphs. Now the question asks us to find the area inside the circle and inside the carryoid. So inside the circle and inside the carryoid. So we're looking at this this area here. So how do we actually calculate that area? So that area will consist of 2 areas. So the first one is this darker region here. So I'm talking about the semicircle on the right, half of the semicircle on the right, and then the remaining one, right? So this area is easy to set up. Now we just need to set up the other part here, right? Now, so I will write. Sometimes it's better to draw the picture than to describe it. So we have a semicircle on the right, and then kind of her shape on the left. That area is equal to the area of this one, and then the area of the semicircle on the right. Right? So after all, even all of that, we still need to determine the boundaries. So boundaries. So boundary here, what we're looking for the boundary is what will be at this point and this point. So it's easy. We will let them equal each other. R equal to 1, and then R equal to 1 plus cosine theta. Make them equal. So we can solve for it easily. Cosine equal to 0, and so theta equal to pi over 2, or 3 pi over 2, or furthermore if we need to, but those will be pi over 2 to 3 pi over 2. when we can find the area like that, notice that because of the symmetry, we can cut everything in half. So in that case, if we do this, we have 2 times the area of only the upper half, and then 2 times the area of the upper quarter. So what I'm talking about is this. First we will have this part first. Double that we have upper and lower of the circle, and then we have the other side. Double that we have upper and lower, and we add all of them up, we have the area of the whole thing. Right. By the way, right, so let's set up what is the area of this quarter circle. Now first, let's look at this first. 2 times the area of the quarter of the circle. Now, we know here this line is theta equal to pi over 2, and this line theta equal to 3 pi over 2. But in this case we have just half a circle, so this is from 0. So for a quarter of a circle, we will go from 0 to pi over 2. And then inside will be 1/2 outer function. So we look from the inner on the outside. We only see the one function at the circle. Will be 1 square. And there's nothing in the inside. So we have 2, 0, pi over 2, and that's just 1/2, right? Now this one we actually can do. So 2 and 1/2 cancel out. So we just have 0 to pi over 2. D theta will be just theta from 0 to pi over 2. So substitute in here, we have pi over 2. So the area of the whole thing, so this area, or 2 times that, is equal to pi over 2. Did that make sense though? Now, we can always confirm that if we want that half, if we want this, the whole right side of the circle is 1/2 pi r square. Pi r square is the whole circle. This is half of that, and because radius is equal to 1, so we have 1/2 pi. So that's why pi over 2. So it makes perfect sense. The area of the circle, the semicircle on the right, is equal to pi over 2. So all of this are pi over 2. Now, we will calculate 2 times the area of that little segment there. Now let's focus on this. Again, we still have 2 because we have 2 of them. Right, now if we want the whole thing, it will be from pi over 2 to 3 pi over 2. By the way, I didn't graph it because that is easy, but now let's just graph it. We have 1 plus cosine theta and then 1. Yeah, I changed windows from pi over 2 to 3 pi over 2. You see, we have that, and then the other half. Now, but if we only want this upper half though, this is between pi over 2 and 3 pi over 2. It is going to be pi. Between pi over 2 and 3 pi over 2, we have pi. So how about we just graph from pi? From pi over 2 to pi. You see, we only have the upper half. So if we want to, because of symmetry, upper half is the same area as the lower half. So we calculate 2 times the area of the upper half. The upper half we only go from pi over 2 to pi. And then if we look from the inside and looking out, we only see the one function from the carryoid on the outside and nothing in the inside. So we have the carryoid will be 1 plus cosine theta on the outside and nothing inside. So we can cancel those. Pi over 2 pi 1 plus cosine theta square d theta. Right. So we have pi over 2 plus this. So the answer will be the area of that. So we're going to add this. And this. Add those two together. We have the area of that shape, including the one on the left and the one on the right. So 2 times that, 2 times that. Right, so in that case we can set up the area that plus that. Yeah, I said it's difficult to describe it, so sometimes I just try to draw it and then we say the area of that portion. A picture tells 1,000 words. Right, so that is that one. Next, we find the area inside of the circle and outside of the carryoid. So inside the circle and outside the carryoid. So we're looking at this one right here. Yeah, inside the circle, outside of the carryoid. Right, so we need that area. Right, we did find all the boundary, right? Boundary here. Theta equal to pi over 2. Boundary at the bottom. Theta equal to pi, 3 pi over 2. And then this pi right in the middle. So we're trying to find the area. Right, so again, I'm going to draw that instead. So the area of that. How do we draw this? Okay, outside the circle, and then the carryoid. Right. So trying to find the area of that. Now, because of symmetry, we can find 2 times the area of just the upper half. Upper half meaning this. Right. So we already find the limit pi over 2 to pi, right? In fact, that's what we graph. Pi over 2 to pi. In this, we have this graph. Right? So the limit will be pi over 2 to pi. 2 times don't forget in the formula for the area we have the 1/2. And then the outer radius square minus the inner radius square. So now we look from the inside, looking outside, looking out. Which one do we see first? You see the function of the carryoid first, and then we see the circle later. So the carryoid is inside, the circle is outside, so we have the r equal to 1 is the outside function, and the inside function comes from the carryoid. Now think about this. Since theta from pi over 2 to pi, that is in the second quadrant. In the second quadrant, cosine is negative. So 1 plus cosine is going to be less than 1. So that's why it makes sense. The radius here, the r here is bigger than that. On the graph, we see when we're looking out from the center and looking out, we see the carryoid first, and then we see the circle. So that's how the integral, that's what the integral is. Of course, the 2 and the 1/2 can cancel out. Just have from pi over 2 to pi, and 1 minus 1 plus cosine square d theta. And that we set up the area of the whole thing. Here we can only find 2.5 multiplied by 2, have the area of the whole thing, here. Right. So that I said at this stage, setting up is focus on the part where we're setting up the integral a lot more than actually evaluated. So always try to find boundary. We need to know the limit of it. While we know the limit, put in the calculator. Make sure we actually draw that part of the graph. Right. Now this will be easy. Set up the integral to calculate the area inside the circle r equal to 4 sine theta. I need to clear this function. Okay, zoom out. Right, how about the limit here? Originally, let's just go from 0 to 2 pi. Right, so look like that. Let's zoom in yeah, usually from zoom in we can zoom where the center is. I will zoom right at the center around there. Now that's a nice circle. Of course we can graph it if we want to. Just going to graph that too. So we have a circle. Close enough. The axis though do not go to the center. The center is here. So it will be like that. 2 and then 4. Right, that's nice and all. Right. We still need to set up the boundary, right? Boundaries. We will set this equal to 0 because we start from here and go back to that. Right. So I have sine equal to 0. On the unit circle, a sine is the y values equal to 0. So sine equal to 0 is there and there, which is 0 or pi. So theta equal to, we just say k pi, multiple pi. 0 pi, 1 pi, 2 pi, 3 pi, 5 pi, doesn't matter, multiple pi. So we just say from 0 pi, 2 pi, and 3 pi, and so on. However, if we just want to want one revolution, I mean one circle here, the boundary will be from 0 to pi. Right, now let's graph. Wow, how about just from 0 to pi? From 0 to pi. Yes, that's enough. Now how about we just cut in half? Because this is symmetry, right? We have the half. So if we want to set up the area of this half, so area of the whole disk is equal to 2 times the area of the half. And the area from the half is integral. In that case, we set up the limit and we see it goes from 0 to pi over 2. Yeah. Instead of go from 0 to pi, we cut that in half, just go from 0 to pi over 2. And then we have from the center looking out, and from the center looking out. We see no function inside, we only see function on the outside from the circle. So the outer function comes from the circle. And there's no inner function. And even this is the last example, I still forgot the 1/2 here. Don't forget that in the area formula, that's this the 1/2 there. So that cancels with the 2. And this one square 16 sine square. Right. Power reducing. sine square is equal to 1 minus cosine double angle divided by 2. Let's take the 16 on the outside. Sine square 1 minus cosine of 2 theta over 2. Take the 2 on the outside from the bottom. 16 1/2 0 pi over 2, and we just have 1 minus cosine of 2 theta d theta. Right, so that gives us 8, and then integral of 1 is theta, integral cosine theta is sine of 2 theta over 2 from 0 to pi over 2. Right, put in pi over 2. And then sine of 2 times pi over 2 divided by 2 minus 8 times 0 minus sine 2 times 0, which is 2 0 over 2. Right. Sine of 0 or 0 of this go to 0, and this is sine of pi, also 0. So we just have this is equal to 4 pi. So the area of that equal to 4 pi. Now this makes perfect sense because this is the circle. Radius of 2. The area is pi r square. The radius is 2. So it's 4 pi. And exactly 4 pi is what we get. When we find the area in the between the polar curve, just make sure you rod and try to find boundary. And when we have the boundary, put in a calculator to see if actually that part of the polar curve that we have. Now, when it's correct, when it looks like exactly what we want, put in the integral and do the area. It's going to be limits, and then 1/2 outer function square minus inner function square. And we just do the math. The integral should not be that bad. Right. Now to finish this section, I will do something that. So now this will go way back to chapter 6 when we're trying to find the arc length. So let's just try to draw the idea here. By the way, this might be in the problem calculus 3, but simple enough. So we'll just do it here. So I have the function, and we're trying to find the length from here to here, right? And earlier, so if we want to find the area, we will chop that up into a small portion. Let's say we just find that portion and then that portion. So when we chop it up, each portion is ds. So the s is the length of the whole thing equal to, we're going to add up all the area of ds. ds is the length of a small portion. Now if I zoom it out, a portion will look like this. And we will have dx and then dy. So ds is equal to Pythagorean identity, Pythagorean theorem is equal to square root of dx square plus dy square. Right, now what we do after that is we multiply and divide by the same thing. Dx square. Now if I divide by dx square, because y is a function of x, that's why we divide by dx square. If we do that, we have to multiply back dx square, right? And the dx square, we can take it outside of the square root, so the integral will become one, and y dy by dx square, I can just write dy over dx square, and then dx taken outside the square root, it becomes just dx because the square root and square cancel out, and dy over dx is the derivative. So this is exactly what we have in section, I think, 6.5. So this is in 6.5, in section 6.5. Now we do the same thing, but we start from this. But this time both x and y are function of theta, so we start from that. So now we have s equal to dx square plus dy square. Now instead of doing that, we will multiply and divide by d theta square and then multiply by d theta square, and take the d theta outside. We will have square root derivative of x with respect to theta square plus derivative of y with respect to theta square. D theta coming outside, d theta. Right, so we just like that. Now I'll focus on the inner part. So we have derivative of x with respect to theta square plus derivative of y with respect to theta square. Now we just focus on the inside here. Inside the square root, that is. Now we know the derivative, so we have the derivative square, right? So we take derivative first and then we square the derivative. Remember, if r equal to r theta, so it's going to be r cosine theta derivative square r sine theta derivative square. Furthermore, r is the function of theta. The function of theta cosine theta derivative square r sine theta derivative square. So do that, we will have product rule. derivative u prime v plus u v prime derivative of cosine is negative sine. I don't have enough space here, so try to conserve space and change this to minus. Yeah. So derivative of cosine is negative sine, so I will start to minus sign here. And then derivative u prime v plus u v prime derivative of sine is cosine, and we square. Right, I'll just multiply it out. It's not that bad. Derivative square cosine square. Right. When I multiply them out, I have just a minus b square is a square minus 2ab plus b square when we multiply it out, and if it is a plus, a square plus 2ab plus b square. So I've just multiplied out difference, square over difference and square over sum. Just want to use that. Minus 2ab, that times that, derivative, and then the function cosine and sine, and minus b, plus b square, function square sine square. Right, so that's the first square. Now I'm going to square the second. A square derivative square sine square. Now plus 2 times a times b derivative function sine cosine, and then plus b square, the function square cosine square. Right, can we simplify anything? And the answer yes. What we have here is minus 2 times derivative function cosine sine, and then plus 2 times derivative function sine cosine. So those cancel out. Next, combine like terms. I see that both of these terms have the derivative square, and then cosine square plus sine square. So factor that out. Then we have cosine square plus sine square, which turn out to be 1. So that turned out nice. Simplified a lot. And then next, we have the function square and then sine square plus cosine square. Cosine square plus sine square is 1. So this turn to 1, this turn to 1. And so when we just have this equal to derivative square and then the function square. So bottom line, the arcing formula for polar curve and let's say the limit here will go from alpha to beta. Theta equal to alpha to theta equal to beta, and we just have derivative of r square and then r square d theta. Right. Just I think it's simple enough. Could be in calculus 3, but it doesn't matter. But the math is simple. I just want to review. Now we see on the arc length, it's just the whole plane. We chop that into a little segment. It's just a straight segment. So ds, we have dx and dy, Pythagorean theorem, and then we just work it out. In this particular, we have x is r cosine theta and y is r sine theta. Take derivative, and then just simplify everything and give us this formula. Right. With that, I stop this section here. Thank you for watching.